So EM waves is one of the topic which we didn't complete in the volume 1, right? So there's a scientist called Maxwell. So what he found was, if you had a capacitor like this, if you had a battery connected like this, again this is one of the topic, just like your volume 1 topics. The notes in the book is very hard to read, okay, so make sure you take the notes properly. So when the current is flowing here, so what have we said earlier? Whenever there is some current flow, there is some magnetic field, right? So we said electricity and magnetism are something like twin sisters, they always come together. So whenever there is electricity, there is some magnetism. Whenever there is some magnetism, there is some electricity. Okay. So if you go back, we talked something about atomic magnets. What is atomic magnet? What is atomic? What is magnet? Nobody remembers anything from your magnets chapter. Each atom behaves like a magnet. Why? Because electrons are spinning. Electron spinning means what? Charge is moving. Whenever there is charge moving, there is a magnetism. So that means that is what is called atomic magnetism. Okay. So whenever there is some charge movement, it will produce magnetism. Okay. So remember we did something like rev by 2, right? Rev by 2. What was that? M. What is M? Magnetic moment, magnetic dipole moment, right? So magnetic dipole moment M is equal to rev by 2, right? So whenever you have so this is my nucleus, the electron is spinning around like this. So that means current is flowing like this. So when the current is flowing like this thumb will, so the electron is going this way, current is this way, which means current is this way, which means thumb shows this way. So that is my north. So it is south. That is what is called atomic magnet. These atomic magnets is what is giving rise to the magnetism property later on. Okay, that is just an additional part. So let's come back to this. So whenever there is some current flow, right? So if I keep a magnetic compass, what will happen? There will be a deflection. Okay, we have seen this many times. Okay, so whenever there is some current flow here, there will be a deflection, which means there is a magnetism, right, around the current. So between the capacitors, with this DC current supply, right? Between the capacitors, is there any current flow here? We have to go back to the principle of capacitor. Is there any current flow here? How does the capacitor work? So when you put plus here and minus here, what is it doing? It's pulling one of the electron from here, then depositing it on this side. So when you pull an electron, what happens to this side? It becomes plus. That's the principle of capacitor. Okay. So the plus is pulling the electrons and then depositing it over here. Next electron pulls it and puts it over here. So that's why this number of pluses should be equal to number of minuses. But is there anything happening in the center? Nothing, right? So there is no direct flow of current through this one. Okay. So, however, so that's the principle of capacitor. But suppose if I know what they did was, they kept a small magnetic compass near the capacitor. Okay. So we know that the current is flowing here, the current is flowing here, but there is no current flow here. Okay. But still, what they found was, to their surprise, there was a deflection here also. Okay. So there was some deflection here. Okay. So this is what led to the understanding of, okay, the present understanding of, so suppose if I take this as the loop, right? So which law gives you the magnetic field around the current carrying conductor? Bayes what law, correct? Anything else? Ampere's circuital law. So this is your circuit, right? I mean Ampere in loop. So at this point, if I want the B, So you should have studied something called integral of V dot dl is equal to mu naught I enclosed. Okay. This is very similar to what? The static. This is for moving charges. Static. Gauss law, right? Gauss law, what is Gauss law? Phi E is equal to Q enclosed by epsilon naught. Instead of 1 by epsilon you have mu naught. Instead of static charge you have moving charge. Moving charge is nothing but current, right? Instead of E into A you have B into dl. Okay. What is electric flux? E into A. Electric field into area. That is electric flux. This is B into dl in the Amperian loop. Okay. So that is integral of this thing. So this is given by, so at point 1, this is just an additional stuff just to remind you. At loop 1, Ampere's circular law gives the magnetic field. Ampere's circular law gives the magnetic field. This space I am going to call it as 2. And this arrows represents the magnetic compass. So at 2, right? So capital is so at 2, if I use this integral of V dot dl is equal to mu naught I enclosed. Is there any current flow here? No, right? So I enclosed will be 0. So suppose if I take a small loop around here, okay, that's the best I can show. It's actually, so if I have a capacitor like this, so listen here carefully. So if I have a capacitor here, I am saying the loop is like this. Okay, that's the best I can show it in 2D. So it's something like perpendicular to this page. Perpendicular to the page. So if I take the loop here, is there any current flowing through this capacitor? No, right? So the current I enclosed will be 0, which means if this is 0, so integral of V dot dl is equal to 0. So that is 0. See, if this is 0, V is also 0. Magnetic field is 0. But what did I say with the magnetic compass? There was some reflection. So that means the theory says that it is 0 magnetic field, but then in reality you are seeing some magnetic field, right? So take it down properly. At 2, Ampere's circular law says B is equal to 0. In reality, in the capacitor, there is a magnetic field. That means Ampere's circular law says B is 0, but Maxwell found that there is some magnetic field inside the capacitor, which means there was some discrepancy. Maxwell identified there is a discrepancy here. So what he said was there is something wrong in the Ampere's circular law, or maybe it works for the wire there, but it doesn't work in the capacitor trace. So he said that it needs some modification. So what he we did was, how do we produce electric field from your EMI chapter? What did we do to produce electricity? To take the magnetic field and do what? Changing magnetic field, right? Remember that experiment where we took a magnet and then moved it close to the solenoid, right? So when the magnetic field is changing, there will be an EMF produced. So that means changing magnetic field produces an electric current. So take it down. So what Maxwell argued was, Maxwell argued changing magnetic field produces electric field. When I say electric field, it is producing some plus and minus on this side, which means when you connect it outside, it flows like a current, right? So electric field or electric current. Okay, for your understanding, I'll give it as electric EMF or current. Actually, it's an electric field. What law was that? Faraday's law, right? By symmetry in nature, he argued why can't changing magnetic field produce electric field? Why can't a changing electric field produce magnetic field? Somewhere else we have talked about something like this. By symmetry of nature, somebody argued something. What was that? Remember? It was like this, why can't this be like this? Which one? Light wave, okay, very close. Photon, okay. Dual nature, who are we there? Next person, who was that after Einstein? He studied second part, de Broglie, right? So Einstein said light is behaving like particle. De Broglie said if light wave can behave like particle, why can't particle behave like waves? And that's what we call it as matter waves, right? De Broglie waves. Okay? So he also argued based on symmetry in nature. So why can't a changing electric field produce a magnetic field? So now tell me. So when I switch on this, right, when I connect this, when the process kind of increasing slowly here, so what is changing? What is this plus and minus? Electric field, which means electric field is changing. So that's what he argued. So he said that if changing magnetic field produces electric field, why can't the changing electric field produce a magnetic field? Okay. So there is a long derivation for this. Okay, I am going to skip the derivation for now and then give you as a small notes later. But let's focus on the main parts first. So based on that, what he found was so this is the basis of Maxwell's electromagnetic wave theory. So take it down as this forms the basis for electromagnetic wave theory. skipping the derivation, but I think it's simple only. You can finish up quickly. So whatever I am writing here, I wouldn't say it is like optional, but it is given in the book. But I don't see they are asking it in the exam. But let's try to understand the derivation. Modified Faraday's law. So if you're going to take physics in college level, probably you will be studying all these things again. So you know that EMF is minus d phi by dt, right? Change in magnetic flux produces the EMF. Okay, when you say EMF, what is that? Voltage. Voltage means what? Plus and minus. That is what is the electric field. So do you understand, right? Somewhere in your second chapter, you have studied victory is equal to education, head, right? So V is equal to yield. But I told you there is another form for this, calculus form. What is that? E is equal to minus dV by dl, dr or dl, whatever it is, right? So that is the calculus form. So this comes on this side, so E is equal to dV by dr. So I don't remember if it was dl or dl, doesn't matter, okay? That's a minus. So I am going to bring this on this side, so E dot dl is equal to dV. If I want voltage V, I have to integrate it on both sides, right? So if I integrate it on both sides, delta will go away. That means E dot dl. So voltage is nothing but EMF, right? So E is EMF, okay? Don't think it is a electric charge. Okay? So at different places, different thing. The same letters means different things. So now in place of this, I can put regular E dot dl minus d phi by dt. I think this minus and this minus is kind of removed, so that's why I am not showing the minus. Is still there, okay. I think I will have to minus. So now look at this. This is changing magnetic field, this is electric field. So changing magnetic field produces electric field, right? So that's what we are trying to show here. So this is what you have studied as Faraday's law, and Maxwell did a little bit of modification to that. That's what is called modified Faraday's law. So changing magnetic field produces electric field. And so that's the first part, modified Faraday's law. Second part is derivation is actually very simple, but it's a bit lengthy. Let's see. So the second one would be electric flux by E is equal to E dot A. You know this, right? Electric flux is nothing but electric field into area, right? That is what is called electric flux. This take as a side note, only then you will understand this is separate and this is a main derivation. So this part is over. So now we are talking about the second part, the symmetry in nature. So this is one part, this is the second part. I know victory is equal to A, which means E is equal to V by D. So that means I can say V by D dot A. Q is equal to quantity is equal to curriculum by day. So Q is equal to CV. So that means V is equal to Q by C. For C capacitance of the capacitor, we have studied a formula, we came up with the formula. It's like R is equal to rho L by A, C is equal to epsilon naught A by D, right? A by D is your geometric property, area and distance, D. Epsilon naught is your medium property, right? Medium distance. That means Q by epsilon naught A by D, D, A. So what happens to D, D? A cancels. So I get Q by epsilon naught. What is this? Phi E. I am going to say differentiate on both sides. Means I get d phi E by dt is equal to 1 by epsilon naught is a constant, so dq by d. What is q by t? Charge by time. Current, right? So that means dq by dt is equal to epsilon naught comes on this side, so epsilon naught d phi E by dt. So Maxwell gave a new name for this because this is current term called as IED. So it's called displacement current. So just below this, take it down. I don't have space here, so I write down. So ID is equal to dq by epsilon naught d phi E by dt. Changing electric flux, or I can say electric field. Causes a current term. So the changing electric field causes a current term, which is called displacement current. Whenever there is some current, what do you know? There is some magnetic field. So that means what Maxwell argued was, inside the capacitor, if you do this, right, all these things was for the capacitor. So take it down, right, for the capacitor. For the capacitor, he said that all these things are for the capacitor. So inside the capacitor, he is able to come up with the current term. It's not really current, not actually a current, but it's called current term, dq by dt. So here I am going to write as not actual current. Below current term, take it as not actual current. Which causes the magnetic field. So far what I have shown is changing magnetic field produces electric field, which you already know, but Maxwell did a small modification. Then he took the capacitor, all these formulas you already know, so he just played with all those formulas and he came up with the current term. So what he said was, even though there is no current inside the capacitor, you are getting a current term. So he called it as displacement current. It's something like, so carefully listen. So if I take a capacitor here, right? So if the electron is moving from here to here, I would call it as movement of charge, which means it is a current. But in capacitor, what's happening? Electron is not going from this plate to this plate. It's going from all the way around the circuit and going to this plate. Following? So that means current is not this way. It's going to the other side, but it's not directly going this way. Following that? So he called it with a different name called displacement current, because it is getting displaced. Charges are getting displaced. Okay. So that means, earlier what did we say? We said there is no current, which means the Ampere circuit law is not working correctly. But now he said that by doing this, he said that I can assume that there is some displacement current. Okay. So let's see. So this one I would say, this part alone, mark it as like plus star. You have to study, but I don't know how they will ask you. So after this, I will give you some notes, so take it down properly. Very often they will ask you in the 2 months, 3 months, everywhere they will be asking. Okay. So this, whether you study it or not, whatever I am giving after this, you have to study it properly. Okay. So can I erase this side? Anybody still copying this?